we've defined the voltage or the electric potential is minus integral E dot ds. And we also said that was the change in potential energy per charge. Okay, well, that means that the change in potential energy is going to be Q times V. And so that turns out to be an interesting sort of thing here. So change in potential energy, that's going to be joules. Okay, and so we can figure out the energy of something. Well, so if for example that we've got a battery, let's imagine we have a battery, and so the battery provides a current, and so we have a current of 12.5 amps, and we run it for 3.5 seconds. So let's say this is a 12-volt battery. Okay, then I want to know how much energy was dissipated. Well, we look at it and say, well, gosh, how do we do that? Well, we want to find out the energy dissipated, so the energy, the change in energy will be Q times V. Well, how do we find Q? Well, we know that current times time is going to be Q. We remember that from the very first chapter. So that was from chapter 21. And so that means the change in energy will be 12.5 amps times 3.5 seconds times 12 volts. And so all we have to do is multiply that out, which is a total change in energy of 525 joules. Okay. Well, sometimes you also want to know power. So power is the rate of change of energy. Okay, so that would be the rate of change of QV. Now, if the voltage is constant, that's going to be dQ dt times V, or in other words, that's going to be current times voltage. Okay, so again, you have a battery here, and you've got you connect it across, so you got 12 volts, and you've got 3.2 amps. Okay, then the power would be 3.2 amps times 12 volts. So the power coming out of that would be 38.4 watts. Okay. When you buy electricity, you buy electricity as a kilowatt hour. So what's a kilowatt hour? Well, that's 1,000 watts times an hour, which is 3,600 seconds. A watt times a second is a joule, so a kilowatt hour is 3.6 million joules. Okay, so that's what they charge you for electricity, typically is kilowatt hours. And so not so much the power as the total energy usage. Now, these are all very large energy. We're talking about lots of amps. We're talking about, long time. There's also very small bits of energy. So if you have a hydrogen atom, you got an electron up here, and you want to pull the electron off, that takes very little energy in there. And so the energy there is extremely little. And so you really only takes a few volts to do this. Okay. And we define a very small amount of energy as, you have an electrical potential here, so delta V is 1 volt, and so we move an electron through 1 volt. Okay, so the electron changes 1 volt. We know that the change in energy is going to be Q times V. Okay, well, if we take the absolute value of that, then the absolute value of Q is going to be E. So the change in energy is in E times V. Well, the fundamental charge times voltage. Okay, in fact, a name to that. We call that an electron volt. The electron volt is EV. That's the energy it takes to move one electron 1 volt. So you multiply this out. 1.602 times 10 to the minus 19 coulombs times 1 volt. So an EV turns out to be 1.602 times 10 to the minus 19 joules. Okay. So you only take, a little over a dozen EV to pull an electron off of a hydrogen atom. Well, that's assuming it's a ground state. If it's an excited state, it takes only a few EV. And so there are other units here that we use sometimes. And X-rays, then often the X-rays have a certain characteristic energy. And so sometimes you have other units besides an EV. An EV, 1.602 times 10 to the minus 19 joules. But X-rays have a characteristic energy that's a KeV, or a kilo electron volt. So what would a KeV be? Well, it'd be 1,000 EV. So that means a KeV would be equal to 1.602 times 10 to the minus 16 joules. Okay. Occasionally, you have high energy things that are MeV. So an MeV would be 1,000 KeV. So it'd be 1.602 times 10 to the minus 13 joules. Okay. When you're talking about nuclear physics, where you have particles and antiparticles annihilating each other, they give off energy that's characteristic of giga electron volts. And so that would be equal to 1.602 times 10 to the minus 10 joules. Okay, so there's several different related things to the EV in terms of energy units. And again, we get used to this. And again, as a student, I wanted to keep track of units to keep track of things, so I had to write all this down too. So sometimes subatomic physics, we talk about the energy of a beam of electrons. And so we have these electrons, and we'll say it's a 655 EV beam. What does that mean? It means each electron has an energy of 655 electron volts, or EV. Well, how much energy is that? Well, if it's moving here, that means this is kinetic energy. So the kinetic energy is 655 EV. So we know that kinetic energy is 1/2 mv squared. Okay. And so that means that the velocity is going to be the square root 2k over m. Okay. And so all we have to do is figure out what is that. Okay. So 655 times 1.602 times 10 to the minus 19 joules. Okay. So that means the kinetic energy here, 655 times 1.602, 10 to the minus 19, is going to be equal to 1.05 times 10 to the minus 16 joules. So we plug that into here. So that times 2 divided by the mass and electron. Mass and electron is 10 to the minus 9.11 times 10 to the minus 11. Okay. And when we plug that in, we come up with 1.52 times 10 to the 7th meters per second. Okay. So that would be how you would find, and again, the mass of an electron is 9.11 times 10 to the minus 31 kilograms. Okay. It's one of these numbers that just sticks in your head after you do it a whole bunch. So that means if you say that your beam of electrons is a 655 EV beam, then that means that the electrons are going that speed, right there. Okay. Now, it gets a little bit more complicated when you get into the KeV or MeV, which is mega electron volts, or the giga electron volts. Okay. Then what happens is that it gets a lot more complicated, and you end up with a whole bunch of other sort of problems, and then you have to include special relativity. we could actually find the velocity of this. And so the velocity